we were at the determination of carbon. And just before stopping, we've seen that here we have calculated the amount of oxygen that is removed. And multiplying each line the oxygen, the total oxygen, with the percentage which is of reduction. Okay. This means that in the reactions, the reaction consists in removing this amount of oxygen, 25.3 kilo, using carbon. Then it is the question, there are two types of oxygen that we remove. The one is from MnO2 to MnO. This is removed using CO. And the main one is an oxygen removed in MnO using C. But actually the CO reduction, the CO gas comes from this. So it is the same carbon, but it is the same carbon, but instead giving only CO, it is higher oxidized to CO2. So when carbon is oxidized in CO, there is a ratio chemists use. They say in CO the O over C ratio is 1. This you understand. 1 oxygen for 1 carbon. Actually they say the C over O. Okay. And when you have CO2, when you form CO2, here the ratio C over oxygen is 0.5. The same is in MnO, the Mn over O is 1, and here the Mn over O is 0.5. Okay, so to calculate the amount of carbon, we must indicate this ratio, because of course if you transform all carbon into CO2, you will need less carbon to remove the oxygen. This you understand. And you see here we have indicated this is an input. We have indicated 0.6 CO. And so it calculates the carbon necessary for reduction, just saying that it is the oxygen oxygen multiplied by 12 over 16 carbon over oxygen and multiplied by C over O.
C12 is carbon bond. 12 by
C is carbon, and you see, let's assume if I have here, if I put 1, that means that all that carbon is transformed only globally to CO. And that means then this value 18.9 is nothing other than take 25.3 times 12 over 16. I guess this should give 18.9. Can you check?
How can we determine the ratio?
Yes. Yes. I explain. But did you understand this calculation? So let's go back to what did we have, 0.6. And I will explain, I will respond immediately. When you give this, at the same time, you give this, which is the PCR, post-combustion rate ratio, which is CO2 over CO plus CO2. So, giving this is equivalent to giving this. But the number is not the same, of course. Because you understand, it's a formula. It is given here. If you want, I can demonstrate. But if you want, you can find out yourself this evening. It's not difficult. You see, there is. It's a simple formula. There is no other cell than this one. So when you give this is simply calculated. But why these numbers? You can imagine if the simple case, if I put here 1, PCR is 0 because you have only CO. And if I put 0.5, PCR is 100%. Okay? Do you need to demonstrate that formula? It's a mathematical.
Yes, would you explain about?
It's better. I mean, this is not so important. This you can find yourself if you, and if you don't find, I show you, of course. But what is important is why do I put this, or which is equivalent? Why do I assume 80%? This I explained a little bit yesterday. It depends on the configuration of the burden. This is the coke. This is the ore. And this is coke floating over the slag, because you understand why coke will not penetrate into the slag. And this is the slag. So, why in the case of ferromanganese do we assume a good PCR? The reason is because we have three positive points. The one is the amount, the height of ore. In ferromanganese smelting, people traditionally use a high burn, meaning they not only have a rather high slag amount, but also they charge ore in order to have a high ore height. Because of course, if you charge it having only this, you understand that the CO bubbles coming out here, these are CO bubbles coming out when the reaction takes place. If you have only this amount of ore, or if you have practically only slag, you cannot produce CO2. Because CO has no time to further react. That's the first reason. It's height of ore. Of ore layer. The second reason is the second reason is that and in the ore we have MnO2. MnO2, as I explained, easily reacts, meaning that when you find MnO2 here, it will easily react to MnO. And for instance, I told you that, maybe you remember, that chromium and manganese have a similar behavior, but that is a difference. If I have in the ferrochromium furnace, it's not at all the case. You don't pre-reduce Cr2O3. You don't pre-reduce it. In case of Cr2O3, this component goes until this, and then it is reduced at once. But I made myself some tests in reduction furnaces, in pilot, small size, and for this the objective was to see can we pre-reduce Ca2O3 at solid state prior to being melted. The answer was no. We heated up some. We had some pellets of ore, and we heated up the pellets until. No, the exact number was we heated up until 1350. We had no pre-reduction, and once we tested 1400, and then we had pre-reduction, but it began also to melt. The result was exactly this. It began to melt, and showing that it began actually. Yes, I forgot to say that the atmosphere was CO atmosphere because we had carbon beside. But carbon does not touch. It is the CO from the carbon which reduces. And you see, at 1400 it began, the pre-reduction began, but also melting began. And then we also destroyed the refractory of the Earth, or of the pilot. Okay. So in case of chromium, definitely the PCR will be 0. But in case of manganese, because this is pre-reduced very easily, you have a good chance to make this reaction and CO giving CO2. So, CO. That's the second reason. Easy at low temperature. Okay, and what was the third reason? The height. I don't remember, sorry. These two reasons are strong reasons. Maybe I get it later, I don't know. I had in mind that there were 3 reasons, but sorry, I cannot. So these 2 important reasons make it easy and favor a high post-combustion ratio. So of course this is we will see what is the influence. So you may be wrong, exaggerating it, or you may be pessimistic. Of course, it's not exact science. Okay, then I tell you that there is a method of calculating it more exactly. But this is another small model. It is a model of the layer, you know, because No, the balance that we do is done for all. This is metal. Is done for all this. And actually we make no special calculation for this part, because we assume that the ore is just falling here, cold ore is entering. You remember, we have no preheat of the ore in our system. Now, what we could do is making a specific balance for the ore layer, for the solid ore layer. And then we could estimate this. I would say if we have time tomorrow, or we can do it. It's not so complex. But it's a separate model. It's another model. So I would say if you have these two good reasons, the PCR will be high, more than 60%, and I would say 80%. I have experience of 50% with 50% PCR with a mix with residues, including nickel, manganese, some chromium, but few chromium, it was, the conditions were less good than here, and we had 50% that we could measure, because you can measure if you suck the gas coming out here, you can measure CO2 versus CO.
How about ferrosilicon?
Ferrosilicon, it's the same. Ferrosilicon is more complex.
More complicated?
Because in case of ferrosilicon, no, it's more complicated. Ferrochromium is simple, but the other way. Ferromanganese is simple, this way. But ferrosilicon is more complex because you have SiO2, and don't think that you just reduce SiO2 to give Se. It's not like this. Actually, you have also an intermediate, which is SeO, but what makes it complex is this one is volatile. It is gaseous, and so, but it's not so detrimental, because you can catch it and reduce it again. So if you have a layer, it may be positive, but you see it's just the other way. Instead that having only carbon that migrates, carbon in form of gas, CO, CO2, you have also this. So it's more, it's complex. If you are interested, I can, but I had to prepare because it's more difficult.
But in POSCO we have the ferrosilicon, ferromangan, ferronickel.
Yeah. I mean, ferrosilicon, the balance we can do like this, the global balance. But it would be, if you are interested, I should prepare a specific presentation for the reactions, because it's a bit different. while ferronickel is simple, as I explained.
Ferrosilicon is complicated than other ferroalloys.
Yes, it is also fabricated like in similar furnaces, and also the behavior. You remember the behavior of the arcs, small arcs, is same. So this is same.
Silimangan is more simple.
Silicomanganese is comparable also. It's comparable as well. What is then very different is of course calcium or silicocalcium. This is completely is another word. There, but you have no arcs, etc.
Silimangan is no
No, silicomangan is comparable. Silicomangan, but Sika.
Ashika.
Silicocalcium. This is very different. And I must admit, from this, I have personally less experience. I did not work on this one. But it is not really a with a submerged arc. There are practically no arcs. So these are, I mean, qualitative arguments to say 80% is okay. But as I told you, if we have time, if you want anyway, tomorrow we can demonstrate. Right? We will make manually the balance of this layer. Okay, so we have calculated the amount of carbon that we need for reduction. 11.4 kilo. This is a kilo per 400 kilo, because it's the percentage. We have used the percentage. You agree? So for 1 ton, it would be 114 kilo. Agree? Okay. Then we have an additional carbon that we need to calculate. It is the carbon for carbureting. This is the carbon dissolved in ferromangan to have the 7% target carbon. And this is just this figure is just this one that we already calculated, which is the kilo carbon per 100 kilo ore. Agree? So the total is this plus this, 14.2 kilo. Okay? And now I had no detail on the coke quality, so I have assumed some standard data. So I have assumed 86.5% carbon and 12.3% ash. Of course, this can be variable. And using this data, I say for melting 1 ton ore, the kilo anthracite or the kilo coke is this one times 10, because for 1 ton instead 400 kilo, and multiplied by 100 over 86% carbon. Fine. Okay? And what we find out is 164 kilo, and of course we compare it with the input data, which is for dry coke is 150, that's 149. So the calculation gives more. Why? I don't know. It's comparable, but it's more. And so there must be a reason why they announce less. One reason could be that in the ore you have not only MnO2, but you have also MnO. You understand? In the ore, we assume that all the ore is MnO2. Maybe there is already some proportion of manganese in form of MnO. This may be an explanation. Maybe there are other explanations. Maybe the coke includes more carbon, but that's not more than this. Okay, 90% carbon is not possible in the coke. So, and then we can say, and what if we have the maximum, the best use of carbon possible? This is 0.5. Then we have 100% PCR, and then you see, then we find, you see, 142 kilo coke. Then we are. So this is also an explanation, but okay, 100% PCR. I don't feel it's maybe difficult. So and what if we put 55? Here you see we are close.
멜팅 한 1톤이고 킬로그램 먹으면
You see, that may be also an explanation that PCR is even better.
엔스라이트인가? 엔스라이트. 카본 좀 엔스라이트라서 맞습니다.
Okay.
내가 스펠링이 잘 기억이 안 나요.
You know, sometimes you must accept that calculation gives a different result than you can think about, and you can discuss it. It's good to have this critical view on the calculation.
지금 1톤 멜팅을 위해서 이만큼 포크가 필요하다는 그런 얘기인가?
예.
이게 너무 이렇게 알아보기 어렵게 썼잖아. 그지? 이런 걸 얘기를 좀 해가면서 해야지. 이게 뭔 말인지 다른 사람 처음 본 사람 보면 알 수가 없잖아. 뭐 마크를 하든지 뭐 좀 이해가 쉽게 써놔야 되는데 나중에 그 정리가 조심해서 내가 좀 힘들더라고.
Is okay for carbon?
So
Not okay.
one more explain to the for melting 1 ton kilogram is a rectangle size of 100 and 164. Yes. I can understand.
You don't understand how it's
Yeah,
calculated?
Yeah. It's meaning of this round.
The meaning of that?
Yeah.
Okay.
And
It's
the
a.
other side. Yeah.
I will improve it.
For melting
1 ton ore. The kilo anthracite or coke.
kilo
is this.
ANTHR is N
Ah, you don't know anthracite.
anthracite.
Anthracite is a you may use anthracite instead of coke. Normally it's not done, but in some cases, in this furnace you don't use anthracite. In some other cases, and or you could say maybe a better word is
material
a better word
Coal.
coal or no.
Carbon.
I explain. Char is the right word.
차.
You know the word char?
char.
Okay. This you must know. This because you may find this word in some publication, in some literature. It's rather simple. I explain that coke. This is coke. Coke. No. Sorry. Coal. Coal to fabricate coke is including volatile matter, fixed carbon, and ash. About
수신수. Charcoal. Charcoal.
10%
Charcoal.
about volatile matter is very variable, but to make coke it's about 25%. And this gives coke. So when heating the coking coal, the specific coal giving coke, you fabricate coke, which has practically only the fixed carbon, which has no volatiles, because you have heated in the coke oven plant, you heat the coal up to 1000 degrees, and all the volatiles escape, and you have the carbon fix, and you have the ash. And this is coke. No.
Charge.
If you do this pyrolysis, meaning heating up on coal which is not coking, the result is called not coke but char.
잘. 못해 수수.
So if you have no coking coal, it is called char. Coal char also, coal char or char.
Charcoal. Charcoal.
No. Charcoal is different.
Different?
Charcoal is coming from trees.
Yeah, that's right. And
Charcoal?
char is different.
Exactly. Char, coal char or char is coming from coal.
Coal.
While if you do this, if you heat up eucalyptus trees, you make charcoal like you use for your barbecue. Or like Brazilians use in small blast furnaces, you know, they use charcoal. But this is char, and in some furnaces they don't use coke, they use char.
콜에서 코크가 냉을 차라고 해. 그죠?
But actually the origin is exactly the same. But of course for specialists it's totally different, because coke, you have a piece of coke, you can you don't. It is very resistant. While the same for coming from any normal coal is not so resistant, because it's not made for blast furnace. But you cannot use directly coal, actually for at least two reasons. Coal will escape the volatile matters and it will strongly increase the amount of gas. That's the first reason.
Increase the amount of gas.
Of gas, because the coal particles would, when they are heated up, they would escape, they would fly off the volatile matter, which is hydrogen, CH4, tars, and this volatile matter is not useful here. So it is probably reducing the productivity because it increases the gas, and the volatile matter are not useful. So it's just putting a burden on your, putting a higher job for the gas cleaning. So this is really not good. And no, there is one additional reason, is that this coal would be less reactive. Because heating up the coal very quietly gives a char which is less reactive, which is less good to make the reactions. While how is char produced? Some people say also the coke for SAF furnaces. There are different ways, but the way that was most popular in Europe and in France, I have worked on such kind of furnace also. It is a rotary kiln in which you put the coal, and of course you starting you you put a burner, but just to start, to, how do you say, to ignite, and afterwards actually you put some air, and it's, I don't know whether, I think there is 2 or 3 places where you put air, and then the coal being heated, the volatiles are enough to burn and to, you understand, to make the heating, the pyrolysis, the right word is pyrolysis. Pyrolysis, because pyrolysis means heating without oxygen. Because if you would heat with a lot of air, you burn the coal. So actually you add just a little bit air to burn the volatiles that escape, but it's very few. And in the coke oven is a pyrolysis, and in coke oven, you know, there is no oxygen at all in the charge, because you heat the walls, the flames are behind the walls of the coke oven. Is this okay for you?
Yeah, okay. It's 10. Why 10? times 10.
Ah.
R39
No,
times 10. 10,
Uh,
10 million.
yes, the meaning of 10 is because it is for 1 ton.
Yeah.
While the numbers until here are 400 kilo. Because here this addition for oxygen,
Yeah.
this is percentage, or a percentage is kilo per 100 kilo. And if you want to have it for 1 ton, you need factor 10. You see, here the oxygen, the amount of oxygen, that's the column of oxygen. The column of oxygen is indicated, these are percent oxygen. And percent, and then you multiply by the reduction, and this is a total